Hello Lower 6 mathematicians, this is a video about the geometric distribution. So to start with, let's recap what we know already about the geometric distribution. We know that there are only two outcomes. There's success, which I associate with probability small p, or there's failure, which I have a small q. There are only two outcomes, so therefore the probability of P plus the probability of Q must equal 1. So when I'm talking about success and failure, the question will tell me what a success is, and everything other than that is therefore a failure. So it might be that success is rolling a 6 on a fair die. So if I roll a 1, 2, 3, 4 or 5, even though there are 5 options there, they are all classed as failures. So that's where you get the idea that there are only ever two outcomes. So as I said, recap number 2, probability of P plus Q must equal 1. The next recap is that you keep repeating the trial or the experiment until you get a success, and at that point you stop. So everything up until the point of success must be a failure. So the idea of the geometric distribution is how many goes will you have until you get a success. And at the point of success, as it says, you must stop, or that's the end of the experiment. The notation that I use for the geometric distribution is that, so x is got a geometric distribution of p. So the only thing in the brackets is the probability of p. So let's have a look at an example. I'm going to say that let x be rolling a 6 on a fair die. So that means that the success is rolling a 6. Everything other than rolling a 6 is a failure. So therefore, the probability of success, small p, is 1/6, and the probability of failure, small q, is 5/6. If I were to write this question in this notation here, we would have that x, which I've said is rolling 6 on a fair die, is geometrically distributed with the probability of success p as 1/6, which is in the bracket. If you remember the equation that we've looked at before, this helps us to work out what the probability of getting a success is on a certain number of attempts. So the probability that x is equal to some number is equal to q to the power of x minus 1 times by p. So this is a really key equation here for the geometric distribution. It's easier probably to think about it if we do an example. So let's think about the probability that x equals 5. This means when I roll a fair die, what is the probability that it takes me 5 attempts to get my success, i.e. to get a 6 on a fair die? So because of the idea that you keep repeating the trial until you get a success, if it's going to take me 5 attempts, everything up until that 5th attempt must be a failure. So I have 4 failures followed by a success. And on the 5th attempt, I get my success. So I have failure to the power of 4, and times by, so this is the 5th attempt. This is a 5th attempt times by 1/6. So it's 5/6, because that's the probability of failure on the first go, times 5/5 times 5/5 times 5/5. So that's my 4 failures. And then I get the 5th go, because it's probability x is equal to 5. Then I get my success. So 5/6 to the power of 4 times by 1/6. So with the idea of the geometric distribution, I could have done this on a probability tree diagram. So let's just have a quick look at this probability tree diagram here. So because I've either got success or failure, so I've got the branches of my probability tree diagram are a 6, rolling a 6 or not a 6. If I don't roll a 6, I go to the second roll, and I could get a 6 or not a 6. If I don't get a 6, I roll again the 3rd attempt. Not a 6, I go the 4th attempt. Not a 6, I go the 5th attempt. So I've put the probabilities on this tree diagram as well. So 1/6 is a probability of success, i.e. getting a 6, and 5/6 is a probability of failure, i.e. not getting a 6. So I could have drawn out my tree diagram like this. Now, what I've ringed here is what we had a look at in the last question. So the probability that x is equal to 5, because that's not a 6 on the first, not a 6 on the second, not a 6 on the third, not a 6 on the fourth, and then I get a 6 on the fifth. So 5/6 times 5/6 times 5/6 times 5/6 times a 6, which is what I did on the equation before. Now, there's nothing wrong with doing this, but as I've sort of tried to show at this point here, it can go on forever, because theoretically it might take me, I could roll 10 die, or I could roll the die 10 times, I could roll it 300 times, I could roll it 3,000 times before I get a 6. It would be very unlikely not to have got a 6 by the 2000th attempt, but it is theoretically possible. So this tree diagram can carry on forever and ever and ever and ever, because theoretically, because of the idea that I keep repeating the trial until I get a success, then theoretically I could just keep on going on forever. As I say, that's a very small probability, but it is a possibility. So yes, I could have used a tree diagram, but it's not particularly efficient, and therefore it's better to use the formula that we looked at just a minute ago. But hopefully the tree diagram shows you where the formula comes from, and it helps in our understanding of the geometric distribution. The tree diagram also helps us with another geometric distribution idea, which we're going to move on to now. So I'm going to take a completely different situation here, which is nothing to do with a geometric distribution. It's just a normal tree diagram that you probably may have come across when you were in year sort of 7. Or year 8 or year 9. So imagine that I've got 5 beads in a bag. I've got 2 red beads and 3 black beads. So I take a bead, I record the colour, I replace the bead, and then I pick another bead. So on the first attempt I could get a red or a blue, so I've got 2/5 and 3/5, and then I replace the bead. So on the second attempt, or the second pick, I could get, having got a red, I could have got a red and a black, and again the 2 associated probabilities, and having picked a black bead on the first go, on the second go I could again pick a red and a black and their associated probabilities. So what are the outcomes I could have got? Red red, red blue, red black, black red and black black. And I have listed their outcomes or their probabilities here. So 4 out of 25, so that's 2/5 times 2/5. 6 out of 25, so that's 2/5 times 3/5, and so forth. As I said, this hasn't got anything to do with the geometric distribution, so don't get confused there. But the key thing is that all of these probabilities here must add up to 1. So all of the possible outcomes, if you add them together, they must add up to 1. And that's going to be really, really key when we look at the geometric distribution. Because if I go back to this diagram here, this tree diagram, what it is saying is it's saying that regardless of the fact that this could carry on forever and ever and ever, then all of my different outcomes must add together to make 1. So this one is so here I got success on the first go, here I got failure and then success, failure, failure, success, failure, 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 success. And if I worked out all of these probabilities, even though it carries on forever and ever and ever, because of this point here, they must add up to 1. And that is going to help us with what we're going to move on to now. So what I want to do is now move on to the idea of move back to the idea of geometric distribution, but keeping this idea in mind that all of the probabilities must add up to 1. And I'm going to think about the geometric distribution, and I'm going to think about writing it in a slightly different way. So I have to put this slightly on the wonk. Okay, so I've got some random variable x, and I want to work out what is the probability that I get success in less than or equal to 3 attempts. So let's stick with our die idea. So what's the probability that I roll a 6 in less than or equal to 3 attempts. So what I have done here is I've kind of drawn sort of almost a number line out. So that shows I could have got it on the first attempt, the second attempt, the third attempt, fourth, fifth, sixth, seventh, all the way up to n attempts, because there could have been, I could theoretically not roll a 6. So I have drawn it out like so. And I want to work out the probability, as I say, that I roll a 6 in less than or equal to 3 attempts. They've all got their individual probabilities. So the probability of rolling it on the first attempt would be 1/6. Probability of rolling it on the second attempt, so that's failure, so that's 5/6 times 1/6. The probability that I roll it on the third attempt would be 2 failures, so that's 5/6 times 5/6, so that's 5/6 squared, times a 6th. The probability that I roll it on the fourth attempt would be 5/6 to the power of 3 times a 6, and so forth. So they've all got their individual probabilities. But hopefully you'll see how this idea of a number line can help us when we're answering questions like this. So we know that because of this idea here, that they all have got to add up to 1, so all of these possible outcomes here have got to add up to a total of 1, because of the tree diagram idea before. So let's use this idea to investigate this probability here. So the probability that I roll a 6th in less than or equal to 3 attempts is the probability that I roll it on the first attempt, the probability that plus the probability that I roll it on the second attempt, plus the probability that I roll it on the third attempt. So if I were to work that out, so success on the first attempt would be a 6th, plus success on the second attempt, well, that's 1 failure, and then I get my success, so 5/6 times by 1/6, plus the probability that I get it on the third attempt, so that's 2 failures, and then a success. So if I were to work those out, then I would get the answer of, if you do that on your calculator, 91 over 216. Now, how I want us to think about this is as follows. So the idea is that if I want to work out the probability of it's less than or equal to 3, let's kind of draw like a line here. Okay, so I want to work out this probability here, probability that x is less than or equal to 3. So that is saying that it takes me 3 or less attempts to roll a 6. Everything to the right of that must therefore be the probability that it takes me 4 or more attempts to roll a 6. So because they all add up to 1, because of this idea here, then I can say that the probability that x is less than or equal to 3 plus the probability that x is greater than or equal to 4 must equal 1. So I could rearrange this equation now, and this is going to be the crucial part. So to work out this probability here, that x is greater than or equal to 4, so the probability that x is greater than or equal to 4 is equal to 1 minus the probability that x is smaller than or equal to 3. So it's 1 minus this part here. So this probability is 1 minus this probability. And if I do another rearrangement of it, so probability that x is less than or equal to 3 is 1 minus the probability that x is greater than or equal to 4. So I have these two rearrangements here which are going to be really important because of this whole number line idea.